that's pretty bad. Yeah, I would just. Oh, honestly, like I was a little, I don't know. This was with me water, but I did the fix. Like amend the class. Yeah. So the highest I can get, I get everything. Yeah. Okay. Like explanation. Like it gives you. Oh, I was just more about that.
Also gives you a question.
Sometimes
the question is- and then it gives you a question.
Yeah. So it's
Okay, folks. I did manage to get your test finished graded this morning. I'm going to pass that back. I also did your lab from not yesterday, last week is also graded. I posted that on Blackboard, but I won't hand that back until next lab. But I'm going to go ahead and pass back your test. When you get your test back, the way just a few things. Number one, I mark off how many points you miss per page. And then on the very back of the exam is where it's tallied. So you will see how many points you missed on the back of the exam. You'll see how many points that is, and then how many points out of 125 you got on the test. Now, I did, because of the length of the exam, I went ahead and curved the exam 10 points. And there are some people that, there was one person, I mean, I know it was doable. There were 3 or 4 people that had wound up, because of that 10-point curve, earning over 125 out of 125. So I know it was doable. It was hard. It was long. I will not deny that. But I also am curving this exam. I won't curve other exams. But now you kind of know what to expect from me. And so hopefully you better know how to study to prepare for my exams. So anyhow, when you get your grade back, you're going to see so many points out of 125, and then you're going to see a +10 beside it, because again, I curved everybody's score by 10. So that's the grade you'll see in Blackboard. So I'm trying to stay caught up with y'all as best as I can.
What was the average?
I don't know. I mean, there were a lot of people that made C or better. But I did not get a chance to do the average. I got it done in about 10:15 this morning. So just barely in time to get it back to you today. Which was my goal, is just to get it back to you. As I said, typically I will only keep your exam for 1 week. That is my goal with exams. Now labs, that's a different story. Labs sometimes take me a little bit, but exams, 1 week. So it's big grades, you get back as fast as I can get them to you. Okay, so I think I've got to say the last name here, because I think I've got to. Abby Armstrong. Michael's not here. And I always mispronounce her name. And I'm going to make you say it for me when you get up here. Because I know I've mispronounced it for a semester. Say it for me. Anna. Anna E. Okay. Anna E. Jakira Davis. Seth. I'm going to wait upstairs. Keegan. Peyton. You know what? I could do this. I'll make life a little easier on all of us. JC. Daniel. Matt. Preston. Joshua. Peter. Krista. Aiden. Gracie. Madeline. Maya. Kennedy. And I will be posting this with you hopefully today. Brayden. Emma. Jason? Jaden? I'm sorry, Jaden. Okay. Oh, Jaden. Oh, I forgot to, I got you. Tyler? William? Lacey? Hey. Micah? Casey? Julie? Jessica? Logan? Ashley? Damon? Taylor?
I thought it was early productions too.
Claire? Probably the most missed, besides rushing, which I know some did, the most missed question on the entire exam was question 15, part A, the last one. Because if you didn't read, it said it was out of 50 grams of water, not out of 100 grams of water. When I do post the answer key, check it. I am a human being, plus I've been a sick human being. It does not sound right, but definitely check your answers. Make sure I didn't make a mistake. When I do the answer key, even for the math problems, I go in and I will list out how many points I expect to give for each piece. And make sure I gave you partial credit where partial credit was due. Like I said, I'm human. And I'm not infallible. So I tried, now, one other thing I did want to mention is on page 6 of the exam, when it asks for the temperatures, I gave pretty much 100-point spread. So, you know, because the temperature, they weren't that far apart. And so I gave about 100-point spread of what I said. But it had to be within, because I felt like that could very well be within reason of a slight angle on a line. Any questions for me? Yes.
Can you explain 6?
Can I explain 6? What is number 6?
Oh, yes.
Ionic compound means that it's a metal and a non-metal. And when we looked at, okay, so on number 6, you could even have looked at number 15 to help along. But basically what you will notice is as you increase the temperature, you're going to increase the solubility of an ionic compound typically. There are a few exceptions to that.
That's not what I really slowed it down in part just go up.
Well,
That's a different thing.
that's a different thing. You're talking about boiling point and melting point.
Do you have an answer sheet available with the answers for some of these problems are?
I will post it online. So I don't have, I mean, I will have it. It's just I haven't had a chance to post it, but I hope today to get it posted online so you can actually take the answer.
Thank you so much.
Other questions for me? By the way, just in case you have to take my final, keep each exams. My final basically is stylized after my exams. And my exams start out as a good study guide. So keep your exam and it'll help study if you have to study for it. Other questions? Okay. If not, if there are no questions, then let's get started into today's material. So yesterday, I briefly introduced collision theory. Basically, a reaction cannot occur if collisions do not happen. A reaction will not occur if the collisions do not happen. But the collisions need to happen with the molecules in the correct orientation. And the collisions need to happen with the molecules having the correct amount of energy in order for the reaction to occur. So really, three things are involved in the collision theory. Three things are involved in order for a reaction to occur. Collision with correct orientation and the correct energy. If any one of those three parts are missing, the reaction doesn't occur. You got to have all three parts for the reaction to occur. Now, qualitatively, view energy for the reaction using an energy of activation diagram. In the energy of activation diagram, the y-axis represents the energy of the reaction. The x-axis represents the reaction's progress. When we think about a reaction, typically we think about a forward reaction. So we're going to move from reactants to the furthest left. And you're going to have products to the furthest right. What connects the reactants and the products is the reaction's energy of activation. The energy of activation is the distance between where the reactants start and the top of the curve. That is known as the energy of activation. Now, in this particular diagram, I have drawn one that is exothermic. and energetically favorable. If we can overcome the energy of activation. The reason we know that this one is energetically favorable is because the difference between the products, the reason we know it's energetically favorable is because the products are lower in energy than the reactants. So this would have a negative delta H for its enthalpy. Now, at the top of this is what you would consider to be your transition state. You're somewhere in between the reactants and the products. We can also draw an energy of activation diagram. Again, the x-axis representing the reaction progress, the y-axis representing energy. And if the reactants are lower in energy than the products, this would be considered an endothermic process. Meaning it is not energetically favorable because the reactants are lower in energy. To get the E sub A and everything else, the E sub A is going to still be the distance between the reactants and the top of the curve. But in this case, we can continue that line and we would show that the reactants are lower in energy than the products, and therefore this has a positive delta H. In between the reactants and the products, you still have the transition state. Now, if I were to actually have given information over here, say that's 100 joules, 200 joules, 300 joules, so forth, then you can actually estimate what that energy of activation would need to be. In this case, This energy of activation is probably around 2.5. Joules of energy. We would be able to figure out our enthalpy. Our enthalpy would be approximately equal to 150 joules of energy. All I'm doing is taking this scale and estimating what that information is. Okay, now, any questions about the general structure of an energy of activation diagram? Yes. Yes, that's energy. Other questions? So from a general perspective of an energy of activation diagram, it can tell you whether, number one, it can tell you about the energy of activation. How much energy am I going to need to put into this reaction in order to make it occur? In the case of the diagram sitting here, I'm going to have to put in 250 joules of energy in order to make this reaction occur, because you've got to put in enough energy to get over the energy of activation. Yes, I can force this reaction to occur because I can put in enough energy to make it happen, but it's not really a favorable process. You have to force the reaction because it has such a large E sub A. The bigger that E sub A, the less likely the reaction is to occur, because you have to put in more energy to get over that energy of activation in order to get to the products. Now, energy of activation diagrams can also tell us other information. If you'll recall, I made a comment that when we look at the rate law, if you'll recall, rate laws do not reflect stoichiometry. They are only determined experimentally. I also made the comment that reactions can be a multi-step process. Your energy of activation diagram can represent that information. Again, you have your reaction progress, and that is on the x-axis, and energy is on the y-axis. You start out with your reactants. And you ultimately wind up with your products. But this step doesn't have to be a single step. It can occur in a multi-step process. Your rate law is basically going to tell you whether this thing is likely to occur in one step or whether it's going to take multi-steps. Because if your rate law does not reflect the stoichiometry, then you can guarantee this thing takes multiple steps. Now, when you have this, each of these represents a transition state. Let me do it this way. And each trough is going to represent intermediates. Now you have multiple energy of activations. You have your first energy of activation, which we're going to label as E sub A1. And it is going to be the distance between the reactants and the top of the hill. You'll have your second energy of activation that will be associated with the second step. And it is going to be the distance from where that hill starts to the top of the hill. And then you can have your third energy of activation, which will be that final step. You will still have an enthalpy. Your enthalpy does not change. In this case, the products are lower in energy than the reactants, and therefore it is going to be a negative enthalpy. Now let's talk about what each of these things means. Well, you can look at this diagram now that we've got it all labeled. This diagram says that the reaction took place in 3 steps. We know it took place in 3 steps because there are 3 hills. There are 3 energies of activation. The first step was a relatively simple step. It didn't take a whole lot of energy in order for that first step to occur. We know that because that energy of activation 1 is a fairly small amount. In this diagram, that second step is what would be called the rate determining step, or the slow step. It's the rate determining step or the slow step because it has the largest of the energy of activations. Other things that this diagram tells us is that we start out with our reactants. We undergo the first reaction, and we are going to make some intermediates. Those intermediates are then going to react with something in the second step to make new intermediates. And then those intermediates are gonna react to make our final products. So this is the type of information. So the big thing that is new with this type of thing is, number one, we now have intermediates. Intermediate, just like it sounds, it's the middle. It's middle. Yes.
So would the reaction as a whole just like one energy of activation of all of them added together, or would it only be, you could only say it has three separate ones?
Okay, actually, I'm glad to ask that. So, it has multiple energies of activation. But if we look at the overall picture, it has to get, I mean, that energy of activation, that middle one is going to be the overall energy of activation. It's going to be the toughest thing it has to overcome. Now, how can we overcome energies of activation, folks? One way is temperature. You crank up the temperature, you're cranking up the energy. So a lot of times we put these things under heat to make the reaction occur. Number two, we can change the pressure. If we're dealing with gases, then if you change the pressure, you're more likely to change the energy. The third thing that we can do is we can take our energy of activation, and if our energy of activation, let's say, is not favorable, we can make it favorable by adding a catalyst. In your body, that catalyst is going to be an enzyme. And what a catalyst does is a catalyst finds an alternative path. A catalyst will find an alternative path that is lower in energy than the original reaction. A catalyst itself does not undergo a change. It starts out the same as it ends up at the end of the reaction progress. Which is an important thing to note. So, a catalyst finds an alternative path with a lower energy of activation. A catalyst enters and exits a reaction unchanged. It does not mean that the catalyst doesn't do anything. The catalyst is going to temporarily undergo a change. But if you look at where you start and where you end, the ultimate, starting and ending, the catalyst does not change. It may temporarily change, but it's not going to stay changed. It's going to look like If you're just looking at where you started the reaction, where you end the reaction, the catalyst is unchanged. I'm saying, I want to emphasize that a catalyst enters the reaction. I'm trying to emphasize that in order to help you later distinguish it between a catalyst and an intermediate. An intermediate is made during a reaction. And then used up in a later step. So one of them the catalyst enters the reaction and comes out the same. An intermediate is made during an earlier step and then used up later on. Okay. So how can we determine our energy of activation? We can use the Arrhenius equation. Developed from graphing. The natural log of K, or the rate constant, versus 1 over the temperature. So in other words, if we graph the natural log of K, the rate constant, as a function of 1 over temperature in Kelvin, we can get a linear line. And that linear line that is produced is the natural log of the rate constant is equal to negative E sub A over R times 1 over T minus natural log of A, where this natural log of A is different than the one we've been talking about. This natural log of A is the frequency factor. So we're back to graphing again. You're going to find that to be a very common theme in College Chem 2. We do a lot of graphing. And we do a lot of using linear equations to solve for various pieces of information. So your T is temperature. Your R is your 8.314 joules per mole Kelvin. Your E sub A is your energy of activation. And K is your rate constant. Let's look at an example of how to use this. The rate constant, K, for a reaction was measured as a function of temperature? A plot of natural log of K versus 1 over T is linear and has a slope of negative 7,012 K. Calculate E sub A. Okay, so when we look at this, natural log of the rate constant is equal to negative E sub A over R times 1 over T minus the natural log of the frequency factor. This equation fits with the formula y equals mx plus b. Looking at that, that means that negative E sub A over R is equal to our slope. We are told that our slope was a negative 7,012 K. That is equal to a negative E sub A over R, and R is 8.314 joules per mole Kelvin. So our energy of activation is 58,297.8 joules, or in other words, our energy of activation is going to be 58,000.3 kilojoules. That is the energy that we must overcome for this reaction to occur. On a test, again, you'd be given the graph, you'd be given the equation, all the equations, you just need to know how to interpret the equations. Now, this is if you have the graph. Now you can also do a 2-point equation, and this looks similar to the Clausius-Clapeyron, but it's slightly different. The 2-point equation is the natural log of K2 over K1 is equal to E sub A over R times 1 over T1 minus 1 over T2. So in other words, if you're given 2 temperatures and 2 rate constants, again, you can calculate the energy of activation. This is how we determine how large that hump in the energy of activation diagram is. How much it determines how much energy you have to overcome in order for the reaction to occur. Any questions? Yes.
We would just use this to find the energy of activation, we wouldn't use it to find, let's say, the rate constant.
Typically, we don't use this to find the rate constant. Instead, we use integrated rate laws because they're much easier. Often, most of the time, this is used if we're really wanting to figure out energy of activation. Now, on the optional homework, I did do one where you're figuring out one of the rate constants, and unfortunately, I made it so big I couldn't even figure it out, so I had to leave it. My calculator couldn't do it. So, but normally we use it for energy of activation.
Why is the energy of activation not negative?
Okay, so the question was, why is energy of activation not negative here? It has to do with how this is set up. So when we're looking at the 1 over T1 minus 1 over T2, if I flip those, then it's available within there. Okay. So it has to do with the order of the tester.
Okay.
That's not.
Gotcha. Finding theoretically.
Hold on, folks.
So theoretically, because of finding a change in work for right.
Other questions? Okay, so just so you again know, as of right now, I will not be here on Friday. Dr. Yang will be here. Now, there may be some things going on and that may change, but I won't know until tonight. But as of right now, Dr. Yang is going to be here. He's going to talk reaction mechanisms with you on Friday. Which will finish up this chapter on kinetics, and then we'll be moving on next week into equilibrium, where we'll spend quite a bit of time. I will post the answer key to the exam today. And as I said, please look over it. I am human and I make mistakes. I don't get upset if somebody comes back to me. Look at this, because that's not my style. I know that things happen. So if you have any questions, let me know. I will see you at the latest on Monday.